Let's continue DNS configuration by focusing on reverse zones for both IP version 4 and 6, but before doing so, we'll show you how to create forward entries for IPv6. So we'll navigate towards the bottom and just label this section as forward IPv6 records. So BIND supports IPv6 forward records, and they're implemented primarily as Quad A records. For example, let's navigate to our shell and ascertain the IPv6 address of the local system. And we're going to work on the internal zone and populate the server responsible for linuxcbt.internal and have it propagate. If config returns the IPv6 information that we're interested in. This entire address that you see here is the IPv6 address of the Ethernet interface 0 on this local system. So to create a Quad A record, we would define it like an IP version 4A record, which includes the name of the host, followed by internet type, and instead of a single A, we use Quad A's, followed by the full IPv6 address. We can create a list of these addresses for different hosts on the network and then populate the configuration file. So for the local system, we've got the address. Let's get it for linuxcbt serve 4. And it's another address derived or auto-configured with the assistance of the default gateway, the router. And this will be for linuxcbt serve 4. And we'll also get one for the other box, linuxcbt media 1, which is running SUSE Enterprise as well. And let's copy this, try it again. It's Quad A's, and there's the address. Let's just remove any superfluous spaces. And last but not least, let's create an entry for the router, since it indeed provides all of the hosts with their addresses, because it's configured with IPv6 interfaces. So in a separate shell, we'll SSH to the router using IPv4. And then we'll do a show interface, and it's bound to the VLAN. So if you search through the interface, you'll find it for either the fast Ethernet interface or the VLAN interface. Either or will. You can also use show IPv6 to take a look at it. If you do a show IP interface brief, this will show you IP version 4 information, and a show IPv6 interface brief shows IPv6 information. We're interested in the network that's connected to our local area environment, and that's the third network. That's this network here. So this is the address of the interface. So we'll copy it, and we did so using show IPv6 interface brief. So now we have 4 records that we'd like to enter into the linuxcbt.internal zone. Let's navigate to the shell and find a shell for linuxcbt.internal. And if we dig at 192.168.75.10 linuxcbt.internal ns, it tells us the name servers: serve 1, serve 4. Now since we're on serve 4 and we're in the slaves directory, we see that this server is a slave for the external domain, which means it's a master for the internal domain. So we're on the right server. So let's modify linuxcbt.internal and insert our new records using Control-Shift-V. So the records are in, and then we'll update the serial number so the records get propagated to the remote system. That is the slave DNS server. Save the changes. Kill all named. service named start, and we're set to go. Now we can confirm that the records have been replicated to Linux CBT serve 1 by checking the named slaves directory and examining the contents of the Linux CBT internal file, where we see the quad A records have been replicated. So after restarting the named instance on the primary server, it sends a notification to the secondary server 1 or more, which causes the secondary server to communicate with the primary for updated zone information. So the 6 records have been copied, but how do we confirm that they're working? Well, we know that if we cat etc resolve conf from either of the systems, it tells us which DNS server is in use. So since 199 is in use, and it is the primary DNS server for the Linux CBT.internal zone, we can use a tool like ping6 to test. So test IPv6 resolution using 1, ping6 followed by the name, Linux CBT router 1. We've picked the router 1 address because we don't have an IP version 4 entry for the router 1 address. And also just use dig to search for the type quad A. So dig at, let's say, 192.168.75.10, the quad A records that are in existence. Or just the plain old name and it will come back. Linux CBT router 1. Both records will be returned. Let's carry out both tests. So first we'll ping 6 using DNS from one of the DNS servers, our local system. And this ping 6 will attempt to resolve, and there you see it's resolved the router. And it's pinging successfully. DNS resolution has taken place. Now let's try the dig of the router address to see what's returned. To be sure, quad A's as well as single A's are being returned. For the router, only quad A's will be returned. Now in this case, the single A wasn't returned because it doesn't exist. How about for Linux CBT serve 1? And we're digging at the wrong host, which is the problem. We're on the .10 host, so let's dig at 99. And there, it comes back. Let's also dig for serve 1. Now you notice the difference between these. For the query for router 1, because the A record doesn't exist, we get no information on IPv6. But for the serve 1 address, it comes back with the A, which is up here, IP version 4, that's what we asked for in the answer, as well as an additional section which includes IPv6 information for the host. So it's resolved as we'd like. Now again, to update the router record, we need to change the DNS to include an IP version 4 entry. So let's modify Linux CBT.internal.db. We'll find the router entry, and we'll create an IPv4 entry. And that's 192.168.75.1. We'll update the serial number so that the changes are propagated. Bring everything on one line, as Nano has a tendency to wrap. Kill all. Then service, exclamation service to start named. And then from the remote system, try to look up the Linux CBT router 1 record again, and now it comes back with both the IP version 4 address as well as the IPv6 address. And it's resolving perfectly. So the forward IPv6, just use your quad A records to denote the hosts, and your IPv6 tools such as ping6, traceroute 6, as well as SSH with the 6 option, or any program with the 6 option will be enabled automatically. Now how about reverse zones? They're important as well. So with that said, the features include primarily the ability to resolve a name given an IPv4 or IPv6 address. So this is important, and we should know how to define the reverse zones for both protocols, IPv4 and version 6. So our tasks include 1 to define an IPv4 reverse zone for the local subnet. So that begs the question, what is the prefix for the local subnet? Well, if we go back to our graphic, we'll see that it's 192.168.75.0/24. From this, we can build a reverse zone. And if we navigate to the shell, ifconfig also tells the story. It tells us that our host belongs to a subnet 192.168.75 because we're using 24 bits, and its unique identifier is .10. So based on the prefix 192.168.75, we can build a reverse zone. So it's built from, and we should just note that, reverse zones are built from the prefix in IPv4 subnets. So with that said, A, define zone name. And for our intents and purposes, that's going to be the reverse of 192.168.75 because that's the subnet identifier. The .10 is simply the identifier of the system. When you reverse that, you get 75.168.192, and there's a special domain setup named in-address-.arpa to house reverse zones. This will be the name of the zone as defined in etc named.conf. We'll also create a file which has this name, and in it we'll place reverse entries that are to be resolved. So, with that said, step B, update etc name.conf with this information. New zone information, of course. We'll block it, we won't copy it yet, but on the primary system, which is the serve4 box, we'll nano etc name.conf. We'll navigate to the Linux CBT section, and we'll cut the entire block for the second internal zone using Control-K multiple times, Control-U, and then define the zone using the name that we defined here, which we've just lost the block for. So we'll copy again, return to our shell, and remove the alpha name, linuxcbt.internal, and replace it with the mix or alphanumeric name of 75.168, or the reverse. So with the reverse zone, you define the zone in reverse. Whatever constitutes your subnet, in our case, it's an RFC 1918 subnet, 192.168.75, is what you turn around to create your zone. This server will be a master server for the zone, which means it doesn't need a reference of masters. And instead of storing the file in the slave subdirectory, it will be stored in var named, as instead of linuxcbt external.db, something more intuitive which speaks to the name of this zone. So it's generally a good idea to just use the same name, and that'll be 75.168.192 in-address.arpa.db optionally. So this will read the zone information from this file, providing we've created it. Let's save the changes. Be sure we're in var named, and then we need to create the zone file. Now we've already got a copy of the zone file in the interest of saving time defined on a remote system, media 1. So if we simply SFTP into 192.168.75.100, and after having authenticated, navigate to var lib named, we'll see the various files and navigate into master, and then download the IP version for zone. We also have one for IPv6, which we'll get in a moment. So let's mget this file, exit the SFTP shell, and then nano it to be clear on what's entailed. So here's a zone file. It looks like a forward zone file. It has a time to live for all the records set to 2 days. In a busy environment, you may want to drop this to, let's say, 3600 seconds if things change a lot. And the source of authority, instead of linuxcbt media 1, will be linuxcbt serve4. And the email address of the user to contact, instead of linuxcbt media 1, will be at linuxcbt serve4. But this can be anything. So long as it's in DNS format, it's fine. Let's update the serial information to be 2008-01-2201. And here we see reverse entries. These are old entries for other systems. We'll get rid of a couple of them, the sun boxes, and we'll update the two NS entries. 75, this is just a reference to the domain, by the way. We could use the @ symbol to reference it as well. 168.192 in address ARPA dot second name server is Linux CBT serve1 internal terminated with a dot. And let's fix the other name server entry to be Linux CBT serve4. So now we have two name server entries and one reverse entry for Linux CBT Media 1. Let's include entries for the two name servers. At .10, we've got, for type PTR, by the way, with reverse files, the entries used the record type PTR as opposed to A for address resource. PTR is short for pointer, meaning this IP address points to the following name. So it's a lookup. So .10 is equivalent to Linux CBT serve1 internal dot, and .199 is equivalent to serve4 internal dot. So now we have a fully functional reverse file, at least for these hosts, using IP version 4. We'll be able to resolve at least serve1, serve4, and media 1. We may optionally create an entry for the router. Let's do so. And that's router 1 internal dot. Then we'll save the changes to the DNS configuration file. So now we have the reverse file. We can restart the DNS server. So we've created that, and let's just note that create zone file in var named, update configuration, restart named. And before starting it, there's one error. This file should have a suffix of .db, so let's move 75 to 75.db and then attempt to start it. So since it's running, we'll kill all and then service named start. So now it's up and running. How do we dig using, or how do we perform a reverse lookup using dig for IP version 4 addresses? So we need to test, obviously. Test using dig, and we're going to dig at the host's IP address, or since it's already configured etcresolve.com, digx and the IP address 192.168.75.1 should return the forward lookup name. Let's try this from Linux CBT serve1, a remote system, which happens to have the Linux CBT serve4 box as its DNS server. So now notice when we did a dig for .1, it came back with router 1. Let's try for .10. It's come back with serve1, 100, media 1. So if we cat the contents of the reverse file, we see that we've resolved the following. Let's try serve4 to see how it comes back. That's 199. And it too works. So we're able to look up items using reverse lookup. If we wanted to indicate a server, we'd use dig at the IP address of the server with the X option. But reverse IPv4 is working, and it still causes IPv6 information to be returned because the reverse points to the forward record, which then subsequently points to any other related records, such as one or more IPv6 entries in the zone file. Excellent. So now how about IPv6 reverse addresses? What's entailed in setting up such an environment? Well, it needs, and let's just note, IPv6 reverse addresses, or reverse zones. IPv6 reverse zones require a name.conf entry, so requirements include etc named, just like every other zone, name.conf entry and var named zone file. But the rules are a little bit trickier, and for that we do have an example already set up on our remote system that we can take a look at, and that we can discuss how it actually works. Let's navigate to etc and nano the contents of name.conf on this remote system. We'll find the IPv6 zone, copy and paste the entry into our documentation, and begin discussion. Here's that zone, in addition to the reverse zone. And these zones have been set up throughout other discussions of Linux CBT. So here's that etc named.conf entry. To describe this is the nibble format with zeros expanded. So note, IPv6 reverse zone names are in nibble. Nibble is half a byte or 4 bits. Nibble format with all zeros expanded. So what's required is that you take a look at your IPv6 configuration and turn it around. Let's copy this block and paste it to the shell and compare and contrast to our IPv6 configuration. We'll Control X, and even on the Media 1 box we can do this using ifconfig and then Control Shift V. So, looking at our IPv6 configuration, we see from left to right that we've got, for the prefix which defines the subnet, just like in IP version 4, reverse 2002.4687 db25, and instead of simply 3, it's expanded. All nibbles are expanded to mean 0003. So 3 is equivalent to 0003. This represents the first 64 bits of an IPv6 address. So IPv6 reverse zone names are in nibble format with all zeros expanded for the network prefix portion of the address, which is usually 64 bits in length. And so long as you can turn around your first 64 bits, which defines the subnet, to represent nibble notation, you can write your zone file. And to be consistent, we have stored, or we will store, the file using the same name, the nibble name, 3 dot all the way through with ip6.arpa.reverse. So let's place this zone information into our name.conf on the primary box for the zone, which we're going to label as serve4 since it's running a later version of the enterprise code. So we'll nano etc name.conf, navigate to the Linux CBT section, and insert our new zone. This will be our third zone. So there's the information for the third zone. This is a tertiary zone. In fact, we have a reverse for IPv4 labeled as secondary. So let's just label this as IPv6 instead of assigning a number. IPv6 reverse zone. So again, reverse nibble format is used, starting with the beginning of the address, 2002, which is a reserved 6-to-4 address, followed by all of the nibbles, expanding zeros where necessary, to the end of the prefix. So this means we'll need to ensure we have the file, but we'll download it from the remote system instead of recreating it. So we've updated our conf file, and we're still in var name. Let's re-SFTP into the remote system, then navigate to var lib named, where we'll find the reverse file in the master subdirectory. We'll mget 3*, exit, and then modify the contents of 3*, just to be sure that everything looks well. And we'll change the default name server from NS1 to Linux CBT Serve 4. The email is fine. We'll update the serial number to be 2008-01-2201. And here we have some reverse records for different hosts, including a Solaris box that we use, serve1, SUSE1, media1, router1. Solaris box is no longer in production at this particular point, but these systems are, so we may leave these entries. So here we see reverse entries. Now, where do these entries come from? Let's take, for example, Linux CBT Media 1's entry and analyze it and compare and contrast it to what actually is configured in the IP stack on the system. So in the zone file, include entries using the last 64 bits or IPv6 address or host part, such as the following. So here we see DAA followed by a whole bunch of items. Let's see where we can find that on the Linux CBT Media 1 box. We'll save the changes to this document, and in fact there's one other change we need to make, and that's for the name server. Instead of NS1, it should be Linux CBT serve4, which means we should include an entry for serve1 as well, since it is an optional DNS server, although we haven't set up the replication yet. Now we'll save the changes. So back to the Media 1 box. Let's find the appropriate window and rerun if configured. It's still running. So we see DAA. So where in the address do we find DAA? At the very end, if you reverse the address, you'll see it. DAA4 followed by B1. DAA4, B1, EFF terminating with 020. And here we see EFF terminating with 020. It needs to be fully expanded. So let's just note, when creating reverse IPv6 entries for hosts, reverse or do the following. Reverse the 64-bit portion, and it's usually, but it's not always, of the address that corresponds to the host, expanding all zeros. B, create PTR record based on the reverse nibble format of the address, and then update your documentation. So we've updated our file, and again, since we've already updated etcname.conf, we simply need to kill the name instance and restart it on the serve4 box. So exclamation kill all will kill the name service, and then service name start will restart the service. So now we have a new zone. You can always confirm which zones are loaded by tailing var log messages. Information pertaining to DNS is logged in that file. So now we need to do a reverse IPv6 lookup. Let's create a new line, test using dig. For example, we'll dig -x because x means reverse, and we'll take the full forward IPv6 address of one of our hosts and attempt to get the name from that full address, such as the entry for Media 1, which we know is in the reverse file, which terminates with 4AAD. So this is how you'd perform a reverse IPv6 lookup, as follows. Let's give this a shot from the shell to see if we're successful. And we'll do so from the local system, which uses the remote system as a lookup source. And there we see that long address, which has been expanded to nibble format, which means 4-bit blocks, resolves in the answer section to Linux CBT Media 1. But how about for hosts that we have not yet populated in the document? We have placed Media 1, SUSE1, Serve1, and Router1, but not Serve4. So let's get Serve4's address. We'll ifconfig and try to look it up. And here's that IPv6 auto-configured address based on 6-to-4 technology, which is a way of using your IPv4 address within an IPv6 address, ensuring that it's unique if you're using a publicly routable address. So let's dig x, this address, And notice the question section is proper. It's been converted out to nibble, but no answer section, and that's because the zone file or remote system does not have an entry for that host. So again, we need a reverse entry for this host, and by looking at this we can see how to turn it around. Beginning with the end, it'll be 2.9.6.1 5BEF F, and you'll always find FF FE in the middle, 9.2 C 0 20 in PTR, and this is for Linux CBT, serve for Linux CBT.internal. And we'll just comment this entry as bind will ignore hash marks and then update the serial number to reflect change number 2. Save the changes, kill all, service, and it will tell us that there's an error in the file, so let's modify it. End of input found. Let's take a look at it. We made a mistake with the file. It's reading something incorrectly. It must be this line, so let's get rid of it. And now it starts properly. And then we'll finish up by performing a query from the remote system, this time of the address for the Linux CBT serve 4 box, and there it is. It comes back as serve 4 in the answer section. Excellent. So we've got forward and reverse IPv6 and IPv4 configuration working. It's very straightforward. We've also shown you replication, primary and secondary replication. Just follow what we've done thus far to copy information to and from servers. In the security section, we'll focus on tightening the rules so that only specific servers are able to replicate or download zone information from your server.